Look closely at this face. It looks entirely real, but this person does not exist. This rapid sequence of high-fidelity human features and complex landscapes is not composed of photographs. They are synthetic creations forged from pure digital noise. The engine behind these creations is known as a Generative Adversarial Network, or GAN. It is a machine learning framework where two separate neural networks are pitted against each other in an escalating high-stakes battle. In this landscape, AI evolution happens through a relentless automated tournament, where algorithms are forced to fight each other to achieve perfection. Inside this digital arena, there are two fighters. The first is the forger, a generator network that attempts to build convincing reality out of random static. The second is the detective, a discriminator network that constantly scrutinizes the forger's output against a massive dataset of real-world training examples. Governed by a strict minimax game, their fight is a zero-sum environment where one algorithm's success strictly equals the other's failure. The detective outputs a probability score between 0 and 1 to grade the forgery. The forger then adapts via backpropagation, adjusting internal weights based on previous errors. This severe, continuous adversarial punishment forces the AI to rapidly cross the uncanny valley, that eerie psychological gap where a digital creation looks almost human, but just wrong enough to be unsettling. The initial bouts were clumsy. In the earliest models, known as vanilla GANs, the forger could only manage blurry, low-resolution 32 by 32 pixel shapes as it tried to parry the detective's basic defenses. Then a critical flaw emerged. If the forger accidentally created a single, specific image that successfully fooled the detective, it stopped trying to learn anything new. It would simply spam that exact same image repeatedly to artificially inflate its score. This systemic failure is called mode collapse. It is a catastrophic training glitch where all visual variation dies off entirely because the forger found a lazy loophole. To stop the forger from breaking the game, developers had to intervene and upgrade the underlying architecture of both fighters. The first major upgrade was DC-GAN. Developers gave the networks convolutional layers, specialized filters that act as upgraded spatial eyes, allowing the AI to recognize patterns and stabilize the chaotic training process. Yet a severe resolution barrier persisted. Whenever developers attempted to generate a massive, high-definition image all at once, the sheer complexity caused the forger's network to crash under the detective's intense scrutiny. The breakthrough came with ProGAN. Developers taught the forger to build images progressively, starting at a 4x4 resolution and doubling the size layer by layer. This progressive scaling lets the forger master broad shapes first, like a jawline, before rendering microscopic details like individual eyelashes. By breaking the computational challenge into these escalating evolutionary steps, the forger achieved the capacity to render hyper-realistic, high-definition outputs. Subsequent models like StyleGAN introduced a mapping network. This granted the forger precise control to disentangle specific traits, allowing it to easily mix the physical pose of one subject with the skin texture or hair color of another. This flowchart shows how models like AnimeGAN v2 formalize this style mixing into an efficient, real-time computational pipeline. Eventually, the training reaches a theoretical climax known as Nash equilibrium. This is the exact state where the forger's outputs are so perfect that the detective's accuracy is mathematically reduced to exactly 50%, a blind coin flip. At this point, the forger has fundamentally broken the detective's ability to perceive reality, ending the training phase forever. With the internal detective defeated, the forger's capabilities have escaped the digital arena and are now actively reshaping human industry. This image displays a high-definition, complex nebula. Scientists now use GAN technology to reconstruct blurry astronomical observations of deep space into crystal-clear cosmic data. This grid of intricate MRI brain scans highlights a vital role in medicine. GANs can generate highly realistic synthetic medical data to train doctors, completely bypassing the need to use and potentially compromise real patient records. And this portrait of Hayao Miyazaki serves as an artistic anchor in the creative world. GANs allow users to instantly stylize their own photographs to match the exact aesthetic signatures of legendary anime directors. Generative adversarial networks have become a foundational engine for global digital creation. Because the forger can perfectly emulate reality, it is now used to create unique profile pictures for non-existing people, enabling the automated creation of fake social media accounts and large-scale corporate fraud. Because the AI detective was mathematically defeated inside the simulation, software alone can no longer protect us from crossing the uncanny valley. The resulting crisis of trust forces a difficult question. How can courts, journalists, and everyday citizens rely on digital evidence when they know anything can be flawlessly fabricated? The ultimate forger has been unleashed upon the internet. The burden of detecting the truth has permanently shifted from the algorithms to us.